Yo, what is up YouTube? In this video, I want to take a look at a couple questions that may come up on a linear algebra exam. So it's objectives 5 through 9, and we're going to start off with this question. It asks us to consider the transformation going from R2 to R3, where the transformation is given by this. So we want to find the standard matrix for T. Doing this is simply A is going to be equal to T of E1, and then T of E2, because we have two variables here. So it's going to look like this. And then we're saying that T is going to be equal to AX is T of X is going to output some vector AX. So let's go ahead and find what T of E1 and T of E2 is. So A is going to be equal to, let's start off with E1, T of E1. So T of E1 is going to be T of 1, 0, which is going to be equal to -2, 1, 2. So you just put in that as the first column, 2, 1, 2, -2, 1, 2. And then the second column is T of E2. T of E2 equals T of 0, 1 equals 1, 3, 0. So our transformation T of X is going to be equal to A times some X vector, and this X vector is going to be X1, X2. That's going to be our transformation. And then moving on to the next question, it asks us, we have some transformation going from R2 to R3, and it wants us to show that it's not linear. So there's two properties we can use to show that it's not linear. We can say C of T of U does not equal T of CU, or we can say that T of U plus V equals T of U plus T of V. These are two properties of linearity. If it fails one, it fails both. Well, if it fails one, it's not linear. So let's go ahead and start with the one that's called homogeneity right here. Let's just choose some random arbitrary vectors. So let's say C is 2 and T is 1, 1. So if we did this computation, we'd get 2 times T of 1, 1. So T of 1, 1 has an output of 1, 2 times 1 plus 1 is 3, 1 minus 1 is 0. This gives an output of 2, 6, 0. And now what if we put the 2 inside instead? So we had T of 2 times 1, 1. That's going to be equal to T of 2, 2. If we plug that in, we get 8, because that's 2 cubed. And then 2 times 2 plus 2 is 4 plus 2 is 6. And then 2 minus 2, 0. And now we notice that T of 2 times T of 1, 1 is not equal to T of 2 times 1, 1. These two things don't equal, so it's not linear. Cool. And then moving on to the next bit, it's show that the transformation from part B is 1 to 1. So showing that it's 1 to 1, we want to say that T of U equals T of V implies U is equal to V. So if we plugged in like some arbitrary vectors into this, we'd have okay, so we're plugging in a R2 vector, so U1, U2 is going into here. And then the output for that is going to be u1 cubed 2u1 plus u2, and then u1 minus u2 is going to be equal to, here we have v is v1, v2, and we have v1 cubed 2v1 plus v2, and then v1 minus v2. And what we can do is equate these two things, because we said these transformations were equivalent. So we have that u1 equals v1, because u1 cubed equals v1 cubed, cube rooting both sides gets us u1 equals v. And we can plug that expression into, let's go with this one, u1 minus u2 equals v1 minus v2. So instead of saying u1, let's say v1 here. And we noticed v1 cancel, and we have u2, negative u2 equals negative v2. And then from that, we say that u1 u2 equals v1 v2, as we just proved. So this transformation is 1-to-1. I said 1-to-1 like that. I don't know if you have to. Okay, and then the final one, or not the final one, we got a couple more to go. It says suppose that u1, u2, and u3 are is a linearly dependent set. So let's keep that in mind. It's linearly dependent. And T is a linear transformation. Is it possible for this thing to be linearly independent? So this one's kind of tricky. What I'm going to start with is saying that since these are linearly independent, or dependent, sorry, u1, so c1, u1 plus c2, u2 plus c3, v3, c3, u3 is equal to 0, where not all weights are 0. And essentially what this is saying is this is a linear dependent set. This is the definition. So from there, let's take a look at T of C1 U1 plus C2 U2 plus C3 U3. So an important fact that we're taking away here is that T is a linear transformation. We're saying that this whole thing, this whole transformation, this is equal to T of 0. So using properties of linear transformations, we can break this up to be C1 T of U1 plus, and I think these are all vectors. These are all vectors. Sorry about that. Plus C2 T of U2 plus C2 T of U3 is equal to T of 0. And T of 0 is always going to be equal to 0. And the reason that's the case, so let's see, why is T of 0 always going to be equal to 0? If we input the 0 vector, we're going to get out the 0 vector, because, so this is like saying T of U, some arbitrary U minus some arbitrary U is equal to T of 0. So if we break this up, we have T of U minus or plus negative T of U. And this is just equal to 0. So what we are essentially saying is T of 0 is 0 always. And because that's the case, again, here we have C1, C2, and C3, like we talked about earlier, are non-zero weights. And this is just a linear dependent relationship. So therefore, the set T of U1, T of U2, and T of U3 are not linearly independent. Okay, sweet. Now, moving on to the next question. It says it's a 3x3 matrix A is reduced to I using the following steps. So it wants us to find A inverse. Remember, the process to finding A inverse is we start from A on this side, and then we have the identity matrix on this side, and then we do some row operations to turn A into I, and what we're left on the right-hand side is A inverse. So if we perform these row operations on the identity matrix, we'll get A inverse. So let's start with the identity matrix for 3x3. And let's just start throwing in these row operations in order. So it says R3 plus R1 into R1. That's going to make this 1, 0, 1, 0, 1, 0, 0, 0, 1. And then let's do 3R1 plus R2 into R2. So 3 times R1. R1 is going to be staying the same. 1, 0, 1. R3 is going to stay the same. 0, 0, 1. And then 3 times 1 is 3. Plus 0 is 3. 0 times 3 is 0. Plus 1 is 1. 3 times 1 plus 0 is 3. And then the next row operation, negative 2R2 plus R3 into R3. This yields, let's see, what does this do? So negative 2R2. So R2 is staying the same. We have 3, 1, 3. R3 is changing, and then R1 stays the same. So negative 2 times 3 is negative 6. Negative 2 times 1 is negative 2. Negative 2 times 3 is negative 6 plus 1 is negative 5. And then the final row operation is R2 swap with R3 interchange. And that gives us 1, 0, 1, negative 6, negative 2, negative 5, 3, 1, 3. And that's going to be equal to A inverse. All right, moving on to the next question. Assume that A is 5 by 5 and A squared spans R5. So show that T of X equals AX is 1 to 1. So this is a matrix transformation, and using the fact that, okay. So A squared spans R5. Because that's the case, A squared spans R5. That means A squared is invertible. So the determinant of A squared, which we can re-represent as the determinant of A times the determinant of A, is not equal to 0. Or columns of A span R5. Okay, yeah, so this is not equal to 0. So we can say that these two terms can't be 0. So determinant of A does not equal 0. And because the determinant of A does not equal 0, A is invertible. And by invertible matrix theorem, T of X equals AX is 1 to 1. So this one's like super theorem heavy, but likely you'll have a sheet on your test with theorems on it to help you out with that. And this is the final question we'll go over. It says we're doing 3 interchanges and 4 replacements. So replacements don't change the value of determinant, but interchange flips the sign. So we're flipping the sign 3 times. So we have the determinant of A. So this is them row reducing. The determinant of A is going to be equal to negative 1, flipping the sign once, negative 1, flipping the sign twice, negative 1, flipping the sign the third time, And then now we just need to find the determinant of this matrix. I'm going to expand over the center column because I only see a 3 there. And then I do plus, minus, plus, minus, plus, minus, plus, minus, plus to know the sign of the spot I'm in. Another way you can do that, I've seen people do, let's see, I think it's -1 to the I plus j, where I and j are like the row and column you're in. So this would be I equals 1, j equals 1. And this gives you -1 squared, which equals 1. So right here, we're in 2, 2. So I equals 2, j equals 2, and you get a 4 there, and you're equal to 1. So we can just say a 3, and then we cover these columns, multiply by the determinant 2, 2, -2, 1. So what we end up with is -3 times 2, 2, -2, 1, which equals -3 times 2 plus 4 equals -6 times 3 is 18. And that's the whole entire, well, that's some of the objectives on this exam, and hopefully that's helpful.